going to use. This board was developed by Professor Arturo Mediano, and the idea here is to show how a real RFID system works and the problems that that system can cause for EMC, EMI. Essentially, the setup, this is the schematics of the block. So the setup is very simple. Let me turn on my pointer options here. So essentially, we power the board by two options, either a wall socket, which goes to DC converter, or by battery options, 5 volts. I'm using here a USB cable and connector connected to essentially a battery operated device. Then we have the main board, which runs on a 32 megahertz clock. That goes through a cable that runs an SPI communication bus to the RFID circuits run at 13 gigahertz. Megahertz. So we will see everything on the scanner, and we will see the real chamber results of that board, the problems, and how to fix them. There's another circuit here, circuit number 3, which just come to emphasize the importance of current return loop. I don't think we will get to that in this presentation. It's also available on our EDU kit. Let's focus on the actual live RFID board. So this is the block layout of the board itself. This is actually what I have here. Here it's the DC to DC converter, and this is the wall socket from here. So the power will go through this block and will be converted. This is here is the main processor. As I mentioned, the 32 megahertz, the ribbon cable with the SPI communication, and this is the RFID section. So I have that on the scanner itself, and you connect everything, you take that to the chamber, and then usually you will get something like this. And that's, I assume this is not a good result, right? So the first thing that you will do to try to understand and mitigate the problem is to take a handheld probe and sniff around. So let's do that. Let me switch to the software here. So let's define a new project here. And let's go to live tracking, select the camera. And of course, you can see the board itself. Everything is alive. This is the power, this area here. I'm just focusing on that area because we saw the majority of the problem around 120 megahertz, and this is actually the DC to DC converter. So let's set the frequencies here. 200 RBW is okay, and let's just set the attenuation to 10 here because we are getting high levels. Okay, run, and this is what you see. So first of all, you will quickly do some kind of a really nice and quick scan, and you already see the mountain, very similar to the chamber results. Actually, fairly quickly, we can identify that is the area of issue. So this is actually the coil, and all the circuits of the DC converter, DC to DC converter is around that area. So you can see here that it's fairly quiet. The 32 megahertz area is also active. We can see the signals pop up right here. But essentially, the majority of the problems are coming from that area. So again, this is very easy to understand from that scan. Again, handheld probes. Overlaying the results on the video, and we can see that here. So I stop the scan. We can essentially use the software feature to align everything, see exactly where the emission is coming from. And essentially, this is the first thing that you will do. So now you can see the 120 megahertz mountain. You know exactly what's going on. And let's go back to the presentation. And again, the way to mitigate that is either to create some kind of a shield around the DC to DC converter, decouple it from the main. There's plenty of other of things that you need to do. Or essentially to move to what I'm going to do now is using a battery to operate the same circuits. Everything is the same. So I'll go back to the software. So you can see that it's actually happening in live. So now I'm going to disconnect the cable and connect the USB power. And I'll power the same thing, the same board from the USB. But I'll switch to the scanner so we can take a high resolution, more accurate scans, and you will see the difference. So I'm just connecting the RFID, the RF cable. So this is the way I select or set the scanning. It's going to be just a regular resolution scanning. So essentially I selected that entire area. Just did it before, but that's the way to do it. You select the cable and then the RFID transmission area. Here you're going to select the spectrum analyzer setting from, so in this case, it's from 10 megahertz all the way to 310, 30 kilohertz RBW. Essentially, that will do the trick. So now I can start scanning. And we can see that it takes longer, but in this RBW, but again, we start scanning. First of all, we don't see the mountain that we saw here, right? Around 120, this one is gone. Remember now, this is a battery-powered device. And the environment, of course, is much quieter. So once you do that while it's scanning, we can go back to the presentation and so we fixed the problem. We took that to a chamber and we scan again and we got that. And essentially, this is what we're going to get in the scanner as well. So we solved the main problem, which was the noise from the DC to DC converter, but we still see two area of issues, mainly number 2 here, which we can see that it's 13 megahertz. Now we know what 13 megahertz is. It's actually the RFID, right? So, and we can see it very strongly here. And of course, we can see that it's coming from the antenna. We know that, after all, this is an RFID board. The problem is why we are getting that on the conducted emission test, right? So here, you can actually see that very clearly. So the 13 megahertz signal is being generated here, actually, by that processor here, by this board, here. You can see the IC here. But the problem is that it's actually being distributed through the cable to the main board. And that's essentially caused the failure. So this is what we see here. Sorry. This is what we see here. So we do not expect to see that on the main board in this area here. So again, there are several ways to deal with that, mostly around the board design. One thing is essentially decoupled this cable, the ribbon cable from the main board. You can see while this is an interleaved scan, so the scan continues, and we can see the distribution of that specific frequency to the main board, which is undesirable event. Now, we fixed the main thing, right? The highest point, but let's see if we have some more issues, essentially. So let's go back to the presentation. So next thing is essentially to go to a radiated emission test. So now you connect everything up before powering the system. You do the ambient test, and here you can see the FM radio around 100 megahertz. So this is not coming from that board. Here you can see the fourth harmonic of the 13 gigahertz. Again, cause us to fail, but now we know where it's coming from. This is coming from the antenna. We need to disable or decoupling the ribbon cable so it won't come to the main board and won't affect it. So that thing, where's the mouse? Sorry, I lost the mouse. So that thing needs to be addressed. Then we can see here the mountain of the DC to DC converter. This is around 120, 125 megahertz. And then we have another area here, which is around 240, which makes sense. This is the second harmonic of the switching frequency. Is it? So if we go back to the software, again, the combined scan here, we have this scan here. So I'm talking about that mountain here. So again, these frequencies, I can zoom in into one of them, anyone actually. And again, we can see that it's coming from the DC to DC converter. Indeed. But we have another peak here, around 240, and this is this peak here. This is essentially 244, and this is not coming from the DC to DC converter. This is another, the 18th harmonic of the 13 gigahertz flowing all the way to the main board and still causing us a problem. The problem is that if you have a very high emission from something like the DC to DC converter, you will not see that. Here it's still too strong, so you do see that, but the assumption is if it's the switching frequency is 125 megahertz and you see something around 245, 250, the assumption is that the second harmonic of the switching frequency, but it's actually not. And it's very, very visible if we will go to the battery power. So you can definitely see the harmonics from the 13 gigahertz, from the 13 megahertz spreading around the board. Again, here the DC to DC converter is disengaged, disabled, so we don't see the mountain around 120, and all the activity is actually visible. You can essentially turn off the 3D mode. We can select the cable itself here, and we can see the frequency response or all the SPI activity essentially on the ribbon cable. We see exactly what's going on. All this is very difficult to see when the DC to DC converter is engaged. You can still see that if you know the frequency of interest, right? But essentially the DC to DC converter will mask all the other activities on the board, and it will be very, very difficult to diagnose that. Obviously, we will see points of failure, and then the problem is to investigate where they're coming from. So in this example, you can actually see that even if you know the frequencies, if you know how to follow that or to set it in the scanner, you will be able to see that frequency distributed across the main board. And as I showed you, any questions so far? Nothing. Good. So that was essentially the example that I wanted to share with you, how to essentially run a scan with a scanner and with the near field probe kits and the integrated camera that we have.